Thanks. Well, it's really great to be here. My talk is understanding cryptocurrencies, and I really did my best to make this as dry as possible. Just a disclaimer, I'm here on my own. I don't represent Google, so this is, if you have anyone to blame for what I'm saying, this is all me. All right, so why would you ever want a cryptocurrency? Why would you ever want a blockchain? Probably not because your pointy-haired boss told you. I think, there's a lot of hype around blockchains, and there's a lot of sort of fumbling around to what they're useful for. And I came up with 3 conditions that I think blockchains are useful for. So, and to be clear, I'm talking about public blockchains right now. You always don't trust the other participants in your applications. So if you're working with people at your own company, probably you don't need a public blockchain because you probably trust them. You need to cooperate with them anyway, right? We live in this world. We have to do business with all sorts of people, despite their intentions, and so you need to cooperate. Sometimes it's because you want an audit trail. Most blockchains provide audit trails. There's been some experimentation with zero-knowledge proofs to eliminate any possibility of audit trails, though. So things like Zcash. Unfortunately, that also comes with the condition that you're never going to be able to be sure that the code is functioning properly. So there might be a bug, and someone might be able to invent an infinite amount of Zcash, and you'd never know. Sometimes it's because you want a very low performance general compute platform. But you don't really need to worry about the Terminator and AI taking over because it's really, really low performance. Think like a 1999 Palm Treo smartphone performance. And everyone on Earth is sharing that. On the other hand, it's basically tamper-proof. No one is going to mess with the computation. So you can build something where part of your application runs in your local cloud or in a public cloud, and then part of it runs on the blockchain. Ethereum is the best example of something that supports this. And you put the part that really needs to be tamper-proof on the blockchain, and you run everything else off of it. So I've been talking about public blockchains. Just a word about private blockchains. They're not new. A private blockchain is just another name for a distributed database with change history and access control lists. So you might have heard of Git. Git is a private blockchain. It's been around for decades. So without the economic element, it's really not new. It's interesting. Git is really useful, but it's not new. All right. So let's talk about how these work, these public blockchains. No one's in charge. How could it possibly function with no one in charge? Well, it has something called a consensus algorithm. And the consensus algorithm for Bitcoin and all of the knockoffs of Bitcoin runs on something called proof of work. And later I'll get into something called proof of stake, which is hopefully going to eliminate some of the problems with proof of work, but it's unproven. So you start off by brute forcing a SHA-256 hash, and I'm assuming a little bit of computer science knowledge. Obviously, brute forcing a SHA-256 hash is impossible in the general case. So it's a constrained version of the problem. And you might have heard people talk about the difficulty, which is a number that goes up and down, mostly up with Bitcoin. And so the difficulty is how constrained the problem is. So the miners are looking for a SHA-256 hash. They're running numbers into it until they get an output that has enough zeros in front of it. So basically, you can think of this as a lottery or a raffle, where you get one ticket for each unit of compute power you have functioning on it. And the winner gets paid in Bitcoin. They get what's called the block reward. They also get any transaction fees that are going into that block. So a block takes 10 minutes. All the transactions that piled up in those 10 minutes get to be piled in, and the miner gets to take the transaction fees. And then the cycle starts over with a new block. So the miner broadcasts that block, and it has a hash of the previous block in it. That's what makes it a chain. Each block is built on the previous block. And then the lottery or the raffle starts over. And it's designed so that in Bitcoin, the blocks come approximately every 10 minutes. That doesn't mean that they come exactly every 10 minutes. You can have one that comes 10 seconds later. You can have one, sometimes it goes 40 minutes without one. It follows a statistical distribution. So, we're just coming off a big price spike in Bitcoin, which caused a bunch of hype. Maybe you've heard of Bitcoin at this point. But transaction fees also spiked, right? Because there's a limited size for each block. And so people started bidding higher and higher fees to bribe the miners to put their transactions into the block. This is actually, in my view, an existential risk for public blockchains. If someone doesn't figure out how to get blockchains able to handle higher numbers of transactions per second, then this might be a very short experiment. Well, only a decade or so. But there's a lot of interesting things going on to solve the scaling problem, so I'm optimistic. So I mentioned before the difficulty. That's how hard that brute forcing of the hash is. That adjusts every 2,048 blocks, which, if you do the math, is about every 2 weeks. And so if people are adding a bunch of processing power and the raffle, they're buying more raffle tickets, then the raffle gets harder every 2 weeks. Other cryptocurrencies besides Bitcoin adjust difficulty on a different schedule. Some, like Ethereum, adjust it continuously. Others, choose a different amount of time. But all proof of work has to do this in some flavor, because otherwise the blocks would just come faster and faster and faster as things got more and more popular. So basically, you can think of this as sort of the more people work at mining Bitcoin, the harder it gets. And then Bitcoin also has its own monetary policy. That block reward there changes, and every 4 years, approximately, the block reward halves. So it started off with 50 Bitcoin per block, and then it dropped to 25. Now it's at 12.5, and it'll drop to 6.25 in a couple of years. And then, just for some interesting game theoretic reasons, the block reward is actually not spendable by the miner for 100 blocks. And that prevents miners from playing some games. So that's the cycle starting over. All right. You might have heard of Dogecoin or Dogecoin. I've never been able to figure out how to pronounce this. Maybe someone here can tell me later. It's very similar idea to Bitcoin. The main difference is it uses scrypt instead of SHA-256, and it runs every 10 seconds instead of every 10 minutes. So why 10 seconds sounds better, right? You get more blocks more often. You don't have to wait as many blocks to have your transaction confirmed. So why would Bitcoin not use 10 seconds? Well, Dogecoin or whatever was designed as a joke. And so they didn't really care. But running it every 10 seconds causes a lot of forks. What's a fork? Okay, so let's go back and remember that the thing that makes the proof of work interesting from a computer science perspective is that it's a trust-free solution to the Byzantine generals problem. I don't know how many of you remember your computer science classes, but This is one of these theoretical problems. The idea is that you have a bunch of barbarian generals, and they're gathered around, camped outside Byzantium, and they're going to attack Byzantium. And each of them has a small army. Byzantium will kill their army if they attack, one at a time. But if they attack all together, they'll win. Now the problem is that the different generals don't trust each other. So they might lie to each other and say, you attack Byzantium. No, no, you attack Byzantium. And if they don't all attack at once, they're going to lose. But if they convince someone else to attack, then they'll get all the spoils. If they're able to win and someone else wastes their army. So this is called the Byzantine generals problem. And the consensus algorithm, proof of work, is designed as a solution to this. Remember, we're working with people we don't trust. So a fork, going back to that, a fork is when two or more miners find a block at approximately the same time. Remember, it's a random process. And blocks can come every 10 seconds. They can actually come to virtually the same time. And so whose block wins? Remember, this is a chain where one block follows the other. It's not a tree. So originally, it's resolved in Bitcoin by longest chain. Satoshi later changed that to the heaviest chain, but you can think of it, it's kind of the same thing. So here Alice is a miner. She mines block 1. And then Bob mines block 2. And it's got a hash of block 1, and so far everything's going great. Uh-oh, here's a problem. Alice and Bob, they're not being evil here, they're not doing anything bad, but they both mine blocks 3 at the same time, and they're slightly different, 3A and 3B. So who's going to get that block reward? Remember, that's real money. 12.5 Bitcoin at this point is worth thousands and thousands of dollars, tens of thousands. Okay, so in this case, they both start working on building block 4 on top of their own block. So Alice is looking for block 4A, and Bob is looking for block 4B. In this case, Bob finds block 4B before Alice finds 4A. So now Alice has a decision to make, right? She can either start mining on top of block 4, or she can keep looking on top of 3A and then hope that she finds 5A before Bob finds 5B. Well, she's already a block behind now, so the chances of her catching up and passing Bob are low. So the rational thing for her to do is to stop mining on this one and start mining on that one. So now she finds the next block, we'll say. Maybe Bob did, but it doesn't really matter. So now we've got this, which is called an orphaned chain. And the blockchain in history that gets recorded is this one. Okay. So that's how Bitcoin functions and all blockchains, public blockchains function. But sometimes we want to change the rules. You might have seen something in the news about Bitcoin Cash and Bitcoin, and or maybe there's an upgrade to the protocol. They discover a bug and they need to fix it. So that's called a consensus change, and it functions similarly. It's using the exact same blockchain. The difference is now everyone is running different software, right? They're trying to run a new version of the software on top of the old version. So it works basically the same way. You're running, say, version 1 here. We'll call that old. And then miners who fail to upgrade start mining on this other chain here. But they know that one, they didn't upgrade, so they try to get over to the new version of the software as soon as possible. And pretty soon, the new version of the software has a longer chain, right? So now everyone says, oh, well, this chain is longer, so I'm going to go with the new chain. So that's how upgrades to software happen. It's pretty simple. All right. They can be backwards compatible, these changes. That's called a soft fork. Or they can be not backwards compatible. That's called a hard fork. Hard fork can change any rules. Soft fork always restricts the rules. So it makes things more, more restrictive set of rules means that they're always backward compatible. All right. Sometimes, though, people disagree, right? There's one thing this space excels at, it's controversy. So recently we had the situation where there was a split between Bitcoin and Bitcoin Cash. And the Bitcoin Cash folk wanted there to be 8 megabytes worth of transactions every 10 minutes. And the Bitcoin folks wanted there to be 1 megabyte of transactions every 10 minutes, right? So how do you resolve this? This is computers, right? They can't go both ways. Well, actually they can. It's just they're going to be 2 coins. So when you have an unresolvable disagreement about the consensus rules, you just resolve it with the free market. Why not both? So I'm not quite sure why these things showed up in that order. Sorry about that. Anyway, so you've got old school Bitcoin going along here with the 1 meg blocks. And then the Bitcoin Cash people come along and they say, no, we want 8 meg blocks. And so now you've got both. And they are each valid coins. And if you get sort of a critical mass, you can get the various cryptocurrency exchanges to list them and list them both. And then they start trading just the same way the dollar trades for the euro, Bitcoin trades for Bitcoin Cash, or Bitcoin Cash trades for the dollar or for the euro or whatever. All right. So that's forks. Let's talk about addresses and how we actually end up sending money, right? So in this scenario, Alice wants to send money to Bob. She wants to send Bitcoin to Bob. All right, so Alice has 2 things here. I don't know who here is familiar with private key cryptography, but she has a private key, which she keeps secret, and she has a public key, which she can broadcast to the world. And what she does is, in Bitcoin, she takes a SHA-256 hash of that public key, and that's an address. So, so she goes and she gets Bob's public key, she gets the address, and then she signs a message with her, sorry, went back. Yeah. She signs a message with her private key that announces to the whole world, I'm sending money to Bob, to his address. And because the message is signed with her private key, and she's the only one who has a copy of her private key, she's the only one who possibly could have sent the money, right? So it doesn't matter that she's announcing it to the whole world. The whole world now knows, okay, I'm going to update my ledger and I'm going to say that this money that used to belong to this address now belongs to this address. This money that used to belong to Alice now belongs to Bob. Now you might see one of the reasons why Bitcoin is a little bit scary is because there's an assumption baked in there, which is that only Alice has her private key. If anyone ever gets Alice's private key, they can send money for Alice. So private keys equal control. If you don't have the keys, you don't have control over your own money here. And this is really scary. There's no takebacks. There's no central authority you can appeal to. You can't go and dispute a fraudulent transaction. Someone gets in and steals your private keys, they can take your money. And there's nothing anyone can do about it. So what happens is Alice broadcasts that she's moving money from address 1 to address 2, address 3, and those 2 don't add up, right? So say she has 50 Bitcoin in address 1. She's buying a car. She has 50 Bitcoin. It's a nice car. And she's buying a car for 48.899 Bitcoin. Why did I pick that number? Well, because it makes the numbers add up nicely. So she agrees with Bob. She's going to pay him 48.899 Bitcoin. So she sends 48.899 Bitcoin to address 3. Now, no one knows, except Bob and Alice, presumably, that that address belongs to Bob. That's why it's called pseudo-anonymous. If you ever find out that that address belongs to Bob, if it becomes publicly known, then you can go back and see all the transactions that Bob did with that. So it's pseudo-anonymous. It's not truly anonymous. And then she has a little bit of money left over. Remember, she started with 50 here. So she also sends 1.1 Bitcoin to her own address. And then that doesn't add up. That leads 0.001 Bitcoin going nowhere. Well, that becomes the transaction fee. That's a tip for the miners. And, well, at least back in the day, it used to be a tip. Now it's a bid. Please, please include my transaction in your block. Please. Otherwise, you'll have to wait for days and days, and maybe it never goes through at all, which is kind of annoying. So, all right. I talked before about proof of work. Now let's talk about proof of stake, S-T-A-K-E. So proof of stake is a different scheme, right? There's been a lot of arguments that proof of work is wasteful. In fact, some people have started calling it proof of waste instead. And so, and that's honestly fair. It really is proof of waste. It's who wasted more money, more electricity running through, their GPUs or ASICs. And so maybe there's a better way. Because we already have all of this cryptography built in. We have these private keys. Maybe we could come up with a way to prove ownership of money, and then we could make it a plutocracy. A plutocracy is something where, the richer you are, the more votes you have. And so proof of stake systems are explicitly plutocracies. And what they do is they do what's called a weighted round robin. So a round robin just means you go around each person, and each person gets to mint a block in turn, and they all take their turn. But it's weighted. This is what makes it a plutocracy. If you have more money at your address, remember we were talking about Alice had 50 Bitcoin. If Alice has 50 Bitcoin, and Bob has 2 Bitcoin, and I have 100 Bitcoin, I get to make 2 blocks for every 1 block Alice makes. Alice gets to make a bunch of blocks for each block Bob makes. So it's weighted. I go, Alice goes, I go, Alice goes, Bob goes. And then, it all starts over. So there have been a couple attempts at building this, and so far, frankly, nothing has worked. There are coins out there that claim to use proof of stake, and they all have deep problems. The first proof of stake coin that I found out about, was Peercoin, and it just used this naive weighted round robin algorithm. Well, the problem is there's something called the nothing at stake problem. I'll let you Google for that, because exactly why that's a big deal and causes problems is kind of complicated. But basically, it causes an incentive for miners to not pick a branch when there's an unintentional fork. And that can cause problems because now we don't know which history is real, and that leads to certain kinds of attacks that can cause the whole scheme to fall apart. BitShares, that's this one, took a different idea. They said, okay, well, we can fix Peercoin's problem. We'll make it so that everyone votes for a delegate, and they call this delegated proof of stake. Everyone votes for a delegate, and those delegates mint the blocks and take turns. So they came up with 101 delegates, except that there was a problem. I don't know how many of you here work in security, but there's something called a Sybil attack. And that's where one person pretends to be many people. And it turned out that of the 101 delegates working on BitShares, most of them were the same person. So that's kind of a problem. Because then that person was running out of money. He was one of the founders and his friends. And was running out of money because this was back before, blockchain was the new hotness. And he said, well, why don't we make up new BitShares? We'll just make them up and give them all to me. And then since he was most of the delegates, he voted to do that. And he voted many times. And his votes went through. And all of a sudden, there were more BitShares. And that's kind of a problem. So this space is rife with bad ideas, and unfortunately that turned out to be one of them. BitShares has some other really interesting innovative technology that unfortunately has, I think, kind of been overlooked because of that delegated proof of stake issue. And here's the real problem. These people are coming back and doing delegated proof of stake for new coins. It's like nobody learned anything. Anyway, Ethereum is working on transitioning away from proof of work to something called Casper, which is an algorithm that hopes to fix these problems and render proof of work obsolete. And that will be amazing because the amount of electricity being spent on mining Bitcoin and Ethereum is kind of out of control right now. It's so expensive. Basically the amount of electricity is going to rise until it's equal in cost to that 12.5 Bitcoin. And 12.5 Bitcoin buys an awful lot of kilowatt hours right now. So hopefully Ethereum will succeed in Casper. And then there are some other coins that are also trying to do similar things. And it'll save the environment and make things a lot cheaper and make the price go up faster probably. All right. So now, what are some of the fun things we can do with blockchains? So far, I've talked about this all in terms of just moving money around or moving Bitcoins around. But remember I said there's no one in charge. So someone, after Bitcoin had been out for a while, said, wait a minute, Bitcoin is kind of like a corporation. Not in the legal sense, but in the sense of having sort of an independent existence and being an independent economic actor. So it's kind of the first decentralized autonomous corporation. No one's in charge. It owns itself, sort of. It has employees, right? These are the miners. Well, actually, they're contractors. They're not employees because they start and stop as they please. And they get paid. They get paid in shares of the corporation, right? You might have seen some empty suits on CNBC talking about the share price of Bitcoin. Well, that's silly. Bitcoin doesn't really have shares. It has coins. But you can kind of think of them as shares, actually. And it provides a service. It gets paid to move its own coins around. That's the service it's providing. Hi, I make stock, and for a price, I'll let you move the stock around between you. And that's really all it does. Other coins, so Ethereum's main innovation was that it said, well, this is an interesting idea. Why don't we let people build any decentralized autonomous corporation that can be coded in a programming language on the Ethereum blockchain, and we'll let people build any DAC they want. Sometimes they're also called dApps, decentralized apps. So the customers pay transaction fees to move money around, and they trust that the math that this whole system is built on will hold together. And that's sort of how it works. All right, what's another fun thing we can do? There's actually a pilot going on right now in Vermont where they're encoding title transfers for property on the Ethereum blockchain. And that would be pretty cool because it would really lower the cost of title searches. That can cost thousands of dollars if any of you have ever bought or sold a house. So we're going to use a scheme called colored coins to make this work. Basically, every Bitcoin transaction and every Ethereum transaction, and most of the other coins support this too, they have a little comments field where you can put in any data you want. And the idea is we're going to put a hash of the title of our property, or maybe a car, or anything else that's valuable, that's worth recording. We're going to put that in the comments field. We're going to take a hash of that data and put it in the comments field. All right. Now we can prove, remember, I own my private key, so I'm the only one who could have done that because I created the transaction. Now we can prove ownership cryptographically. We can prove that I owned this at this particular time, or at least I had access to this data. And I can publish a message that says, I'm selling my house to Chris. And now we can prove that I actually, put it out there in the world in a way that can never be changed, that I'm moving ownership of my house to Chris. There's no step 3. Okay, so self-executing contracts, dApps, DACs. There's a bunch of competing buzzwords here. And there's a bunch of competing coins too. And this is Ethereum, and I think that one's EOS and Cardano and Tezos. And some of these might be scams. I don't really know. I'm not endorsing these. But what sort of things could we build? Well, we have a Turing-complete scripting language. Bitcoin doesn't allow loops, so it's not really Turing-complete. But Turing-complete is just a nerdy way of saying general purpose. And we build those contracts, and we allow them to own currency. So in the same way a person can own currency by having private keys, we say this contract can own currency, and it will move that currency around depending on things that are programmed into the contract. And then we charge a transaction fee for each step of programming execution that it takes. Remember, we've got one Palm Treo to share amongst the entire world. So we better charge for use of that Treo. It's pretty expensive. Okay, here's another fun thing we can do. This is called a stable coin. One of the problems that people have when they talk about, the revolutionary things that are going to happen with cryptocurrency is the price is always moving around so much. Bitcoin a couple years ago was under, like $2,000, and then it went up to $19,000, and now it's like $9,000 or $8,000. And we can never write contracts in it if it costs so much, or if it fluctuates so much. If I write a contract that guarantees I owe you 50 Bitcoin, that's going to be pretty annoying to you or me, depending on which way the price moves. So we need something called a stable coin. And creating one of these, it's actually been done, is a key enabler for all sorts of things, right? Because as soon as we have these stable coins, we can build them into these smart contracts, and then we can do decentralized insurance, we can do decentralized, Uber, anything you want, anything you can imagine. This is probably, stable coins is probably a multi-trillion-dollar space. It could displace all commodities and futures trading. A whole bunch of things could be disrupted if we could just build these. So we make a colored coin. We promise, for an example, that it'll be worth $1. Okay? And we back that promise with escrow. We say if you want to buy one of these, you have to give me say $1.50, me being the smart contract, worth of Ethereum. Or BitShares, or Bitcoin, or whatever. Probably not Bitcoin. And then we write a smart contract that says if the value of that Bitcoin or Ethereum drops close to $1, it'll go out and buy those tokens back on the open market automatically, defending the price. So we'll need a decentralized market to do that, to have an open market. But then, because this smart contract promises to do this, it never has to, because people always want to front run it. There's money to be made. If the value of the token gets above $1, well, then you can short it back down to $1 and make money. If it falls below $1, you can buy it and then sell it when it gets to $1. So there's always money to be made, so the escrow never needs to be used. Makes it a self-fulfilling promise. Isn't game theory fun? All right. I've mentioned some of the politics and controversy around this. I really don't want to get deeply into it, but there are a variety of people who are pissed off by various aspects of cryptocurrencies. Some people, the Keynesians, say that Bitcoin's monetary policy will never work. It'll cause a deflationary spiral. Austrian economists say that some of the more inflationary ones will never work. It'll cause an hyperinflation. Permission-free computing can be really scary to people because you can build some downright evil things with it. There's been a lot of controversy around the dark web and buying and selling things that probably shouldn't be bought or sold. And then anytime you pack enough nerds on the internet, you get arguments amongst themselves. So should it be 1 megabyte block or 8 megabytes of block size for Bitcoin? Someone actually called a SWAT team over that. They called in, I guess the politics are so nasty because the stakes are so low. That's what they say about academe. Maybe it applies here. All right, anyway. And forking, the idea that this coin that used to be one coin could become two, could be really scary to regulators because, wait, how do I regulate this thing where anybody can make a change at any time and all of a sudden there's a new coin and everyone who had one of the old coins now has one of both of the new ones? It's really scary. So that's my talk. We are out of time. However, I'm happy to talk at you all you want at the fireside chat, and now we have another presentation.